what I'm going to do this evening, and this is actually just on Tuesday at the office, we saw a little kitty cat come visit us. And so fortunately, we have nice, huge windows. And so it was just right outside and just kind of came along the building. And then it posed. We lifted the sunshade a little bit. It looked back and I'm like, oh, here we go. Let's do this, you know? So kind of a fun sight there. So what I'm going to do is I change things a little bit because of what's happened over the last couple of days in Southern California. I want to talk a little bit about the meteorology behind these extreme, these fires. Personal story, my mom is evacuated from the Eaton fire. She lives in La Cañada, right next to Altadena. She's okay. The house is okay. That side of the fire seems to be a little less active. But yesterday morning at 4 a.m. was a little bit touch and go. She's 80 years old. She lives by herself in a house that's way too big for her. So getting her out of there, getting her a hotel, teaching her on the fly how to activate location sharing on her iPhone. It's like, okay, here we go. So she's okay. But it's just amazing. It just keeps going. And I just ran the Angeles Crest 100, the race from Wrightwood to Altadena this last summer, and just seeing the first 25 miles of the course burned back on the bridge fire in summer, and now Mount Wilson's on fire. And so yeah, I look back at some of the photos this afternoon just from the Mount Wilson. It was 4 in the morning. I was just descending off the mountain, and just some of the memories there. So into more of the kind of the fun stuff, you know, where does winter stand by historically so far? We'll talk about that, and what is the forecast for the rest of winter and spring? We'll look at that. And then what does this mean for things ranging from water supply to snowpack to outdoor recreation later on this year? Again, as a runner, I totally understand people love snow. It's really important for our ecology. But come like April, it's time for it to go and start melting off. So, you know, that's about the time it always snows too, right? You know, March and April, it's always snowing now. Then and then at the end, with any time we have left, my little Ask a Meteorologist Almost Anything. So whatever's on your mind about weather, climate, that kind of stuff, if you have some questions, I may not have an answer and I won't make it up, but I will do my best. So, you know, let's look at Southern California here. You know, basically the story is an extreme wind event, an unusual wind event, not even a Santa Ana. This is something different. And then a long lack of rain. And this is looking at the precipitation percentiles going back to October. So really the first start of the wet season here, and you've got record dry to like basically top 10% dryness across Southern California. So everything is super dry. I mean, when I ran AC 100, that was in early August, and it was in the mid 90s in Altadena at the finish. I mean, it was just hot as could be. And I remember running through the forest there, just thinking, God, these trees just look like they're barely hanging on. You know, it's just so dry, so hot. So, you know, so we have that as the stage setter. It's just really hot. All the vegetation just is super parched. So we can take a look here. Hopefully, this will work. At the current. This is the only slide that I will be roaming up and back and forth here. So those nearby, don't worry. So let's see here. So this is just the straight visible satellite image here. It goes, so you can see the Eaton fire. This is the Palisades one. And of course, yeah, there's another one out on the west side of the valley. So you can see the wind is definitely out of the northeast. So given the forecast pattern, definitely don't see any of that smoke heading up here. It's all pretty much going to go offshore or to the south. But just pretty stunning imagery. And then what is interesting about our satellite is it can actually detect fire temperature. It can detect heat. So let's go to that. And so what you're seeing, this can be useful day and night. So this, you can see the heat from the Eaton fire, the Palisades, and then there's the new fire. And basically the reds are, so actually the Eaton one seems to be fading a little bit, potentially good news. But when you hit the yellows, like on this new fire here, that's intense heat there. So this is really good, you know, for situational awareness for firefighters and first responders, especially if a fire is in a really remote area. So if it's like northern Washoe County, like north of Burning Man, and a fire starts, this satellite actually probably know about it before any human is able to call it in. So we're actually, as meteorologists, able to see this, and we can actually call in a fire report based on satellite information. Now, of course, for these, it's not needed in that case. But the other thing is this goes into our models. So in terms of smoke prediction and things like that, all this data gets fed into those models to know where the fires are. So that's the current satellite. So let's take a look at the wind gusts here. let's see here. So these are the current wind gusts in Southern California. So actually, I mean, there's some high ones there, but they're really not definitely as bad as they could be. So here in the city, even along the foothills here, the Eaton Fire's right here. You know, there's some 40s, some 20s, 50s up in the mountains, but that's actually kind of sort of a normal Santa Ana type situation. Over here by the Palisades Fire, still seeing some gusts around 40, so that's not necessarily good news there. I'm going to toggle off the wind gusts here for just a second, and I think it's useful to think of the topography here. So when you have a typical Santa Ana wind event, what happens is you have high pressure over the Great Basin way up in Nevada, and it kind of shoots kind of a northeast wind from the high desert here, Lancaster, Palmdale, down into Southern California, into the city and into the ocean. So what it does, that wind tends to stay close to the ground, and it actually finds little gaps in the mountains. And so here, the Cajon Pass, I-15, there's a gap there. The 14, you can tell I'm from Los Angeles. I say the, right? It's the proper way to say it, right? The 14 there, and then down into Oxnard. Those are two big conduits for your typical Santa Ana wind event. This event had not only the surface winds, but it had winds aloft. It had winds like at 10,000 feet, 20,000 feet that were enhancing the intensity of the winds. And it actually was very much like the downslope windstorms that we see here in the Eastern Sierra, which we've actually seen a few of this year. That it's a little bit more of a rain shadow. So what happens with that is the winds don't just come through these gaps. They actually just come right up and over the high terrain here. And then right along the leading edge of the high terrain, what happens is that wind comes up and over the mountain and then crashes down like a wave does at the beach. And so where it crashes down and hits those valley areas, that's where you get those extreme wind gusts, 80, 90 miles an hour. So to that point, one nifty thing about this site, we can actually go back and look at historical data. So let's take a look at maximum wind gusts. So Wednesday was the day where things really went off the rails here. So I'll go, basically we're going to look at the daily max wind in miles an hour. Hopefully it comes up here. Sometimes it does take a minute. Ooh, there we go. So now you're seeing a lot more reds. Now let's zoom in here a little bit on LA County here. You can see a 90 there. And all right, let's see. Every time I move it, sometimes it decides to cooperate and load data. Sometimes it doesn't. So, oh, actually, one more thing, because I know there's some even higher ones here. Let's load all the sites. All the sites. Let's be greedy. Let's see all the data. All right. Come on. Now, you know, as soon as I touch it, it'll load, right? So what happens? It's a function of atmospheric stability, and so basically, in those downslope wind situations, there's an inversion, a temperature inversion at the top of the mountain, and so it reflects off of that. So it comes up over the mountain and it hits that and basically bounces off of it and then crashes down into the valley areas. Whereas if you don't have that temperature inversion at the mountains, the wind will go up and it'll kind of keep going up. It won't ever come back down to the ground. So that's something we look for here in Reno. We actually look at our temperatures at the top of Slide Mountain to tell us if that inversion exists, and then we know whether or not that might happen. So yeah, so this is you can see these wind gusts. There's a triple digit right there, and look at that, 80, you know, definitely into the 80s there. But look how widespread this is. In a typical Santa Ana, you would see these red winds, if you will, only here and out here toward Ontario. For the most part, these areas don't see those extreme gusts, but because this is more of a downslope windstorm, that's why it's kind of everywhere. If I remember right, I swore. Let me try and zoom in here a little bit more. I won't stay too much on this longer here, because this is home turf. Come on, I'm gonna do this. I know at Burbank, anytime I fly down to see my mom, I fly into Burbank. I love Burbank Airport. I can't stand LAX, so I go into Burbank all the time. Well, they had a ton of diversions because the winds were so strong. The planes couldn't land on the relatively short runways there. So you can there's the 100. My mom's house is right there. So, hey, we'll take the 32. That's a win, but this is where the Eaton fire started. There's the 90 right there. So, all right, so let's move along here. I'm trying to think here. So basically what we look, we launch our weather balloons and it kind of measures temperature as it goes up in the atmosphere. And most of the time, the temperature of the atmosphere cools as you go up in altitude. There are special circumstances, and this goes into more science than I necessarily have time to explain, but where the temperature actually starts increasing with height again, and then it decreases again. That where it increases with height is an inversion. Now, we often see inversions around here in Tahoe and Reno, but they're really close to the ground. They kind of trap haze and fog. But sometimes the inversions are like at 10,000 feet, 12,000 feet. And so if they're just high enough above the mountaintop, that allows that high-speed wind to come through that gap, and then it reflects off of that inversion and then comes back down to the ground in the valley areas. So that's a key parameter that we look for. All right. So I mentioned, before that. Okay, we don't need all this. Okay. That this wasn't just the surface level winds, it was winds aloft. So what you're looking at here is the jet stream. This is on Tuesday morning, so it's kind of more north-south. And the reds are pretty strong winds, but it gets stronger. This is basically Tuesday evening. This is overnight, basically midnight Tuesday evening. And there's Wednesday morning. So you have this jet stream. Now this is at 30,000 feet, but it's indicative of very strong winds throughout the entire depth of the atmosphere. So you have this plus your typical offshore Santa Ana winds, and then boom, you add those together and you get what happened there. So just for the sake of time, what I did here is I actually ran cross sections through the mountains. So it's a little bit hard to see it. Basically from like Barstow off to the off the coast there. So here's Barstow. Here's kind of the model's representation of the mountains, which is it's smooth. It's a 13-kilometer resolution model. And then here's the ocean. But you can see these high-speed winds kind of shooting that gap between the inversion right there. And then this pool of even higher speed air, sometimes that gets tapped as well, and that can come down in these situations. A typical Santa Ana wind, as strong as it can be, won't have this available to it. So that's one of the key differences there. So, and not to get too much into the weeds on this, but I think it's important just to kind of talk about the differences there. All right, let's go back to why we were originally here, which is talk about this winter so far and what we expect coming in the future. And so you've already seen the graphic on the left there. That's the precip anomalies so far for this winter. It is a story of north versus south, if you will, in the Sierra. The northern Sierra, far northern Sierra up into the Cascades, doing pretty well on precip, but the further south you go and actually into Nevada, a little bit drier than normal. In fact, we've actually expanded the drought monitor a little bit into that D1, that kind of entry-level drought, into parts of western Nevada, kind of where this yellow area is here, because it has been fairly dry. Temperatures as a whole have been warmer than normal, no surprise there. The one exception was November. That was cooler than normal, but October and December were substantially warmer than normal, so it kind of beat out the cool November there. All right, so what's the snowpack status overall? Here's the West. Lots of variability, huh? So we're actually doing okay. There's still some variability in the Tahoe Basin. I'll kind of zoom in here in a minute on that. But we're in the green, which is the 90 to 100, 110% of normal. So right about where we, in theory, should be. Oregon has had all the storm activity. They've had their snowpack is doing exceptionally well. Even up into the northern Cascades, not doing too bad. Flagstaff, on the other hand, they've seen nothing, and that's actually kind of getting to scary levels of how little snow they've had in Arizona. I know there is at least one significant wildfire down there. But as I'll talk about, that's actually kind of a La Nina thing, and we are in a La Nina-ish winter right now. So not entirely surprised, but this is pretty stunning how little snowpack there is. Here are the headwaters of the Colorado, for Las Vegas, Los Angeles, their water supply. It's doing okay. These are the Wasatch in Western Colorado. We're actually off to the races. Like early this winter, October and November, it was like, oh my God, they're going to have so much snow. It was double what they should have been at that time of year. But it's actually ever since then, it's been really quiet. So now they're back closer to an average snow water content. All right, so let's zoom in here on the Tahoe Basin. You can't go wrong with a Snow Valley Peak camera screen capture. Every time I run up there, I always try and find myself on the camera, and I never do. The Peavine one I've gotten myself on, but not the Snow Valley Peak one. So what we're doing here is we're looking at the snow water content percent of normals here. It's the same map as I showed you before, but this is point data. So a couple of things I want to point out here is that the east side of Tahoe is doing relatively less snow compared to normal, compared to the west side as is a general rule. Near Mount Rose at 93% of normal, same at Big Meadow. Near Marlette there, 112, so that's not too bad. The Sierra Snow Lab, 118%, 109% at Palisades, 124% here. So in general, there's been a little bit more of a rain shadow this winter than even a normal rain shadow situation, which is unusual because actually the last, I swear the last 5, 6, 7 years, it seemed like every storm we'd get would just spill right on over. There's no rain. The rain shadow is a thing of the past. No more of that, right? Well, this winter is like, yeah, never mind. We're back to doing that. So we're definitely seeing that. Actually, even at Heavenly, only 83% of normal there. The other thing is elevation. When we have gotten storms, they've generally been on the warm end of things. So our lower elevation snow tells, Fallen Leaf Lake only at 52% of normal, Tahoe City 73%. My wife and I, we took the kids, we drove over to Placerville last Sunday because it had been over a year since we've been to a couple of the wineries that we're club members at, and they're harassing us, hey, come get your wines. So we're like, Sunday, we finally went over it, and it's like, man, the snow just doesn't look that good, at least along the highway, but yet the numbers would suggest, 119, 102, it's like actually pretty close to normal, but I don't know, it just doesn't have that look to it. We did come home with 50 bottles of wine, so we're pretty good. We're good. We're good for the next month. We're good. Yeah. So I don't. You got a 9-year-old and a 6-year-old. You need some boxes. So all right, let's move along here. This is looking at the entire Tahoe Basin, so kind of all these snow tells lumped together, and this is a time series. The kind of historical ranges are the gray shading here. The median is this green line here. The black is where we are at. Now, this is snow water content in inches, 10, 20, 30. So we're, again, kind of right where we should be. And it's due to 2 storms. This is a theme here. We get most of our snowpack from probably a handful, 5, maybe 10 storms a season. It was the one before Thanksgiving. Remember that one? And then a storm in about just before the middle of December. Otherwise, we've just sort of seen little nickel and dime type events. We'll take it all, but it's these 2 big ones. Imagine if we didn't have those 2 big ones, where would we be? So that goes to the theme. That is part of the normal climate here. It's just a handful of large storms do contribute a majority of our precipitation in actually, frankly, most of California and Nevada, for that matter. All right, now looking back at previous years, this is kind of a cool plot for the Eastern Sierra. So this does include the Carson and Walker River basins as well. It kind of lumps all the snow water content pickups by a function of month for each water year. So far, the red is November, the yellow is December, and the little green line is January. So you can see kind of where we are in 2025. Obviously, December was a nice, healthy pickup, even beating last year's December. And actually, that's another theme. We're actually pretty far ahead of where we were this time last year. And you remember how last year turned out. Remember February and early March? So we got a lot of time. So if you're worried about the snowpack, and as I'll show you here in a little bit, we are in a fairly prolonged dry period, there's still plenty of time left to get the goods. And here's an example. Last year, it was all about February and March. Look at that. Imagine if February and March hadn't happened last year. And we were worried, right? By the end of January, like, uh-oh, like what's going on here? This is not going to be good. But we definitely picked it up then. A lot of year 2023 definitely stands out. There's 2017. That was a flood year as well. So a pretty neat graphic by the Natural Resources Conservation Service. They're the ones that run the SNOTEL network. So, all right. So what are we going into? Is it El Nino? Is it La Nina? I already spilled the beans on that one. It's La Nina. So what we look at is the ocean temperatures in this region called the Nino 3-4. It's in the tropics between Australia and Peru, roughly. And so what are we looking at? It's basically this region here. There's lots of blue, so we are cooler than normal, so it's a La Nina state. When you lump all the data together, it is kind of a weakish La Nina. Like these blues could be a lot darker and a lot more expansive if you wanted the really strong La Nina situation. So we're officially in a weak La Nina, and it'll probably be that way for the rest of winter. This is looking back at El Nino and La Nina since 1950. Kind of a neat map. The reds are El Ninos, and the further away you go, the stronger the ocean temperature anomaly. And there's the La Ninas here in blue. So we just came off of a really intense El Nino. So that's another thing we'll take a look at is those transitions from a really intense El Nino to a weak La Nina. Does that say anything about the winter to come? Here, see, this is 24, this is 2016, 2008. Look at this El Nino. Holy cow. That's a Godzilla El Nino. Remember that phrase got used leading into that winter, and we thought California's drought was done. It was saved. We're all going to get a lot of rain. None of that happened. It was like really dry winter, and the drought continued. So that was where El Nino kind of got turned on its head. And you know what happened with that one? I never heard a really good explanation on that. You see some of these La Ninas have lasted quite a long time, several years. So are we in for another one? Well, we shall see. So here's the probability charts. Looking at the likelihood of La Nina, neutral, or El Nino. So here's December, January, February. Well, it's going to be La Nina. As we get into April, May, June, we start to trend toward that neutral phase. Potentially for leading into next winter, it's anything, really anything goes at that point. Would we stay La Nina or would we start transitioning to an El Nino? So we are dealing with a weak La Nina right now. So here's the scatter plot for the Eastern Sierra, including the Tahoe Basin, of wintertime precipitation versus the ENSO state. So your La Ninas are green, your El Ninos are orange, and your neutrals are the gray area. So where are we this year? We're in this box. So kind of the weak La Nina just below zero there. A couple things you notice. It's kind of a lack of the super dry winters. So yay for that. Hopefully we don't set a precedent, right? I've heard the phrase, I'm tired of living in unprecedented times. Can we go back to precedented times, right? Yep. I'd say at the last 48 hours, I would agree with that, definitely. But we've also had some pretty wet ones as well in that same block. All right. So those neutral to weak La Ninas are special. And it's something we've watched here. In general, this scatter plot, if you just looked at all the data, it's like really, there's wet and dry versions of everything. But these weak La Ninas do have a little special place in our heart here in Tahoe and Reno. In general, since the 1990s, these have actually ended up a little cooler than normal, and they've leaned a little wetter than normal as well. So now this is for the whole winter to come. This particular data set is December through February. Now at this rate, January is probably going to go down as a pretty dry month for us. So February better pick up the pace if we're going to link up with this climatology here. But that's an interesting stat because in general, ENSO, which is El Nino, La Nina, largely doesn't have a lot of meaning to us in terms of precip forecasting here in the Sierra. Further north it does, Pacific Northwest. Further south, Southern California, it definitely does. Here, not as much. The other thing too is these weak La Ninas, which is right here, a lot of our high water events have occurred during weak La Ninas. We don't know why, it just is what it is. So that's always, when we were preparing our emergency managers for this coming winter, is like, hey, this might be a winter to kind of dust off your flood plans a little bit, just to be, because the statistics kind of show that. Of course, there's plenty of winters in the weak La Nina space here that have fairly normal peak flows on the Truckee River at Farad, as this graph shows. So again, February, March, even early April, but we still got plenty of time left here. So I mentioned this earlier, that strong El Nino to a weak La Nina, what does that mean? We've actually had 14 similarly large shifts in the historical record, and actually 10 of them have had well above normal water flows on our regional rivers, which indicate busy winters. Not necessarily flooding, but just heavy precipitation or snow melt, lots of that. So are we going to add to that, or are we going to be the fourth exception to the rule this year. So the official outlook for the rest of January, definitely heavily above normal in temperatures. These forecasts are good in a state level scale, but when it comes down to the nuts and bolts, our topography is so varied here that you get a lot of inversions. And we talked the I word is coming out, the inversions, where you can actually stay, these pockets of cool air can stay in the valleys for many days in a row, even though the atmosphere at like 10,000 feet is actually warming to above normal. And that's something we actually talk with the ski areas quite a bit on, because that does really affect their snowmaking operations. It's like super cold in Truckee and Tahoe and Reno, but up at the top of Heavenly or at the top of Mount Rose, it's really warm and they can't really do anything with that. It's above freezing, things like that. We have a lot of those. So that's sometimes where these climate outlooks can go a little bit astray, just because they don't have the resolution to be able to identify those valleys. Probably more important that we're in the equal chances on the precipitation, but I'm going to show you some stuff that's going to head in this direction here when we look a little bit closer. So let's look at those same models for February, March, and April. We're going to be looking further into the future. And so I'm going to show you the 8 main models that the meteorologists that do these seasonal weather prediction forecasts look at. And we're going to focus on our neck of the woods and see what's potentially coming. Again, this is precipitation for February, March, and April lumped together, and anomalies. Obviously, this is dry, this is wet. So this first model, mainly dry, maybe a little bit near normal up toward the Oregon border. Okay. Model number 2, a little bit dry, but definitely drier head to the south. Model number 3, that doesn't look good, especially for LA. Drier than normal, but maybe a little bit wetter up toward the Oregon border. Model number 4, oh, okay, we'll take that one. That looks good. I don't mind some green. I don't know if I want blue, because that can mean issues. So heavy precipitation, flooding, all that stuff. That's not a good one. This one, yeah, a little bit wetter than normal, drier to the south, kind of a classic La Nina pattern there. And let's see how many more of these I have. So there's a little bit drier there, and there's drier. So the kind of the summary is of these for the Sierra. So this is for the entire stretch of the Sierra. 2 are dry, 2 are wet, 4 are dry to the south, and then wet or near normal in the northern part of the Sierra. So kind of a mix there, but that's actually a fairly typical La Nina pattern where it tends to be drier the further south you go and wetter the further north you go. Unfortunately, I-80, Tahoe, Reno, we're kind of in that transition zone where some winters stay dry, some stay wet, and that's what makes our seasonal predictions pretty low confidence, especially going into a winter season. So the official outlook from the Climate Prediction Center for February, March, and April is the equal chances. They just couldn't pick something. So equal chances. I also like to call it equally clueless, right? Anything is possible. We could go back to being wet and cold or staying warm and dry. The one thing I did want to point out here, and I'll get to in a couple slides, is the useful predictability, where I can start telling you, hey, we're probably going to turn wetter finally, is generally about 2 to 3 weeks, is where I can see those really big pattern shifts. The models have gotten good enough where I can start seeing some of that stuff 2 to 3 weeks out. We're not talking any kind of details here. Not saying it's going to be Thursday or you're going to get 10 inches of snow in 3 weeks, but just general pattern changes. Generally getting pretty good. And so we'll kind of touch on that here in a few minutes. There's your, I don't know, I had to find some emoji. I had one of our forecasters who's fairly young got me onto the, how was it? I think it's like Emoji Kitchen or something. It's off of Google. You can basically blend emojis together. And I'd never seen such a thing. And I'm like, oh my God, you shouldn't have shown me this. So here we go. All right. So now the seasonal outlook going into last winter. These are it's kind of a crude analysis. It's very pixelated here, but these are the observations for January, February, March of 2024. So in general, in the West, we're wetter than normal, again, mainly because of March. But we're kind of a mix, mainly near normal to a little above normal on temperature. So what did the seasonal forecast have going into that? Well, it actually did pick out the little bit wetter than normal signal, although it was a little bit too far south. And then on the temperatures there, generally okay, although the expansiveness of the warm anomaly in the eastern US is way more than predicted. Any of you who have relatives in the East know how basically they had no winter last year. I think Hartford, Connecticut was in the 90s in like March or something. I mean, it was ridiculous how warm it was. So seasonal forecast, too good to ignore, but not good enough to use. How's that, right? You know, it's like you should put that should be a bumper sticker, right? It should be on my business card. We'll do that. Can you imagine if I had the meteorologist in charge and then have that on there? Yep. All right. So what about those subseasonal tools? What about those tools that we can start looking at stuff 2, 3, maybe 4 weeks into the future? That's, again, where we start seeing some useful predictability skill, even here in the Sierra. One of the things we look at is this called the Madden-Julian oscillation. And so this kind of is a complement to El Nino and La Nina. The MJO operates on a cycle of basically 1 to 2 months, whereas El Nino and La Nina operate on months, if not years. They can cycle, several years in advance. So what the MJO is generally we're tracking clusters of thunderstorms, kind of highlighted by this blue area, that go from west to east across the equatorial regions of the planet. And they cycle again on that 1 to 2 month interval. And so where those masses of thunderstorms are can actually dictate significant amounts of what happens in the mid-latitudes with the jet stream, the storm track. It can actually drive a lot of hurricane activity too, not surprisingly, being in the tropics. So in terms of something that could influence our weather with a 2 to 3 week lead time, it's something we take a look at. The one thing is it can either enhance El Nino and La Nina. So remember I talked about La Nina has dry south, wet to the north. The MJO can enhance that, can make the north like really wet, or it can actually kind of contradict that. And so where you actually might get some significant storms in the south of the western US, contrary to what a La Nina signal would typically have. So that's the one thing it can do both. Again, helps with the predictability. So let's talk about what we might glean on this coming forward here over the next 2 to 3 weeks. The map might be a little hard to see, but this is from the textbook, the precipitation anomalies for each MJO phase as it goes across the planet. It enters certain phase spaces from 1 to 8. And so in general here in California and Nevada, phase 1 up here is green, a little bit wetter than normal. Phase 3, really wet. So those are the 2 main ones we look for wet weather. And then phase 5 is dry, and phase 8 is also somewhat dry. So this next graphic's going to look really strange. It's like a spiral, but it's sort of the best way of plotting the MJO because it is a cyclical thing. So here are your different phases from 1 all the way back to 8. Here's what's happened. This is December. Here's the end of December, January. So the closer it is to the center, the less intense the MJO is. So it has more limited influence on the global weather patterns. But the further away it is from that center, the more influence it can have on those patterns. So over the next, this green line is kind of the average of all these yellow lines put together here. This last dot is January 23rd. So we're basically from now through January 23rd here is the forecast. So we start entering that phase 1 space. It's like, oh, giddy up. Hey, we're going to go wet, right? Well, it's kind of a very weak signal. If it were more out here, I'd be like, okay, this could potentially influence us toward a wet pattern. We go into 2, and then right toward the end of the period, January 23rd, we're into that 3, that's the one that we like to see for wet patterns here in the western US. So we do at least enter that phase space, but the uncertainty is super high. We have some lines that are way out here, so much more intense signal, which could definitely make us turn wet. Or we have some of the scenarios that stay much more muted, and so the influence would be somewhat limited. So lots of uncertainty here, but at least we're in the game. The storm door hasn't been locked. We have the key, it's still there. So we possibly could see some activity return to the area. All right, how about atmospheric rivers? Everybody's friend, right? These are the storms that give us the goods. This is now obviously they can cause flooding here, but this is where we pick up a lot of our water supply. A lot of our snowpack here is from these plumes of moisture that come out of the tropical regions and into the mid-latitudes, kind of slam into the western US, into the mountains, and it kind of squeezes all that moisture out like a sponge. This is all the rain and snow. Well, sad day for us, at least for the next 2 weeks, there's nothing on the horizon. So this is looking at an atmospheric river landfall probability chart. This is from the Center for Western Weather and Water Extremes. They're down at Scripps. They are like the AR hub. If you want to learn anything about atmospheric rivers, you talk to these guys, you go to their website, you're going to see all this stuff. They do lots of cool tools here. But in this case, unfortunately, the probability of AR landfalls at our latitude is not looking too good. And this is for just entry-level ARs. This is for like your just something, right? And now if I wanted a moderate atmospheric river, well, the news is even worse. So yeah. Now, what this doesn't discount, though, and this is actually pretty common in some of the drier patterns, is these inland storms. So what'll happen is instead of a storm just slamming off the Pacific, it's super wet, atmospheric rivers comes right on in, is we'll get storms that come out of either the Gulf of Alaska or they'll come out, they'll kind of be inland track like from Canada. These are our inside sliders. Probably heard that term before. Those are the ones that drop like an inch or two of snow in Reno, usually at rush hour, causes mayhem, right? Those are the days I do my run commutes because I feel safer on my feet than I do in my car. So when we go into these dry patterns, usually there's a ridge of high pressure off the west coast, and that's the case now. So it can actually send some of these inland or northern trajectory systems into Reno and Tahoe. And you'll kind of see that. Looks like there's some potential for that next week. You've got some 20% chances, kind of nebulous chances for some precipitation here next weekend, not this weekend, but next weekend, which is lovely because that's when I was going to do a nice long training run down in Auburn. So, of course, so the forecast confidence should be high that we're going to see precip because that's when I want to get out and do that. All right. This is kind of cool too. This is from CW3E as well, these experimental subseasonal AR forecasts. So what they're doing is they're looking beyond week 2. So we're looking at week 3 and week 4 type of stuff. So here's the latest week 3 forecast. So this is showing you the number of atmospheric river days per week. And so it's like, okay, 1 to 2. Okay, what does that mean? How does that compare to normal? Well, here it is normal. So good news, at least from the 23rd to the 29th, it's not brown, right? There's a little bit of green here. So kind of a nebulous chance, it does open the door to something wetter. But come week 4, that's where things do start to get a little bit more interesting. You see this anomaly start to brighten up here a little bit higher chance of AR conditions affecting somewhere in the West Coast. Now the anomaly is maximized over us, but honestly it could be anywhere along the West Coast at 4 weeks lead time. But that does kind of pique the curiosity. Maybe that MJO phase 3 might actually pan out in a little more intense fashion and kind of lead some of these wetter storms finally up into our region. So again, those atmospheric rivers, they come out of the tropics by Hawaii and boom, right on into the West Coast. That's what we like to see. 2, 3, 4, 5 of these a winter. Now we start getting more of them. That's usually where we start having problems, flooding, blizzards, snow load issues like we've seen in some recent winters. So kind of day-to-day nuts and bolts of the weather over the next 10 days. This first graph here shows you kind of the best guess of temperatures for a variety of cities within our forecast area from tomorrow to January 19th on Sunday. Lesson number 1, tomorrow is the nicest day in terms of temperatures in the next 10. It's going to start turning colder. We'll probably get some of that cool air from the north, some of those inland trajectories. So we'll start cooling off. So even here at, let's say Truckee, 53 tomorrow, high of 29 on Monday. Whew. That's, and then also on Monday, the probability of wind gusts greater than 40 is also kind of at its highest point as well. So yay for that. It's going to be cold and windy. So that sounds fun. I think, yeah, maybe I should do a run commute on that day. That'll be a good time. And then here's their odds of precipitation greater than 1/10 of an inch. Again, probably hard to see, but I want to highlight here, there's some 15s and 20s out here toward the 18th, 19th, and 20th. So again, that following weekend, it does at least open the door to us getting some light precipitation. But at this point, we're not seeing anything major. These would be kind of more north flow trajectory type storms, nothing really wet off the Pacific Ocean as those atmospheric river charts had kind of intimated. So what's our snowpack projection going forward? This is a nifty graphic from the NRCS that takes our, again, this is our snow water content for Tahoe. These are those gray boundaries of extremes that I showed you earlier. Here's the black line. of our observed snow water content. Here's the green line, which is the median. This little X marks the spot as the typical median peak. I don't necessarily have a good explanation for why it's not here, but it's somewhere there. Snow analysis is not my area of expertise. I just use their data. Yeah. So what do we got going here? So what this is neat is what they do is they take our current snowpack and then use past years to then project forward what might happen. So let's look at the 50th percentile going forward. So basically, if we had an average winter for the rest of the winter season, what would we be? We'd be tracing on this green dotted line here. So generally below the typical median, but then we kind of catch up with it as we melt off the snowpack in April and May into early June. So let's see what else we got here. Now these are the other traces. So this is if we had an absolute insane rest of winter, the maximum. So we'd probably be pretty hard pressed to set new records on snowpack at this point. If we totally just kept flatline, we just didn't have another big storm the rest of winter, we potentially would be dealing with some record early melt out scenarios. But again, this is like the first percentile. So there's like a 99% chance this wouldn't occur kind of scenario. This is the 50th, and then this is like the 99th percentile up here. So putting all of that together, there is a 40% chance that we hit the median peak SWE in the Lake Tahoe Basin. So not too bad, right? Not great, but not too bad. We're in the game. You know, it's not like 10 or 5% at this point, but not too bad because we want to hit this X here. This is the 70th percentile here. This is the 50th, so we're somewhere in between there. So that will we get to the 40% chance coming up here. So what does our water supply look like? So we take all that snowpack information, we project the climate going forward. What does our water runoff look like? Well, into Lake Tahoe, about 87% of normal. And this is in the April, May, June, July, typical melt-off period. So again, not great, but certainly not 2015, 2014. You remember those years where we hardly had any water coming out of the mountains. There's 89% at Farad. Carson River Basin, a little bit less in the 80s up in the headwaters, but only 68% at Carson City. Now, the one thing with these forecasts is they do fluctuate from day to day. And this is the forecast for the Lake Tahoe inflow here. It definitely fluctuated. Here's October, November, December, January 1st. So you can see how the forecast has fluctuated. And so if we do start entering a very wet period, you probably see this forecast start to go up. The useful skill of all these water supply forecasts really doesn't get going until February. So this is sort of just a very initial best guess, a WAG, if you will, of what we expect for water supply going forward. But honestly, once we get into February, once we've had a good chunk of winter behind us at that point, then these water supply forecasts do actually start to carry more weight and have more meaning. So you can start assessing like, oh, if I go, if I do the TRT in August, am I going to have any water? That kind of stuff. During some of those drought years, I remember running the east side and some of the streams that would normally have water, it was like early June and they were already just dry. So that was fun. I'm like, oops, well, I guess I don't have any water. So that was what was that? I think I did Carson up to Snow Valley and then down and then off of Genoa. And my wife met me down here and I was just so parched. She had the best cold watermelon that I've ever had in my entire life. It's right there. I remember it to this day. All right, so a little bit of bonus here before we kind of wrap up with a Q&A and whatnot is I want to plug this DRI experiment that is it's a citizen science project where you can report via your phone the precipitation type. It's a really neat experiment. It automatically knows your lat long via your phone. It just uses a web browser. And this data gets sent to DRI, and then we use it, among other entities, to ascertain where is it raining versus snowing. And especially as the climate's changed and Lake Tahoe is no longer all snow all the time, it's rain or snow, having this kind of real-time information is super, super valuable for us. And I use it on the forecast desk back in December when we had the storms, just to assess the rain-snow situation around Tahoe. think I was doing some aviation forecasting. And it was just super helpful to know, okay, it's swapping back and forth between rain and snow. What's kind of interesting is in this screen capture here, one of the people that was participating in the project was driving, hopefully not driving, hopefully passengering, along I-80, and you could see the change in phase. So in this particular case, the grays are snow, the pinks are rain or snow, and then the blues are rain. They've changed it since a little bit more, kind of, I think it's green and blue. But it's kind of neat, you can see exactly where it switches over. So a really neat project. Is a very easy way to help us out, to help DRI learn more about rain versus snow lines and where to forecast them and how to assess them. So highly recommend getting involved in that. We did update our mountain weather page. This is generally for the backcountry and avalanche forecasters, but it's useful for really anybody doing mountain things in winter or summer. One that we added these, kind of mentioned the probability information. So like what is potential high end of snow most likely, or what is the low end of snow in a certain 12-hour period. You can graph the snow level, elevation as a function of time. This is an example from Mount Rose Highway Summit. So if you just take a picture of that, you can see, go straight to that. I tried Googling NWS Reno mountain weather and it didn't really go to that. So Google hasn't found it yet, but really neat page where you can dive into some of the data for the Tahoe, and basically Tahoe, Mammoth, and the White Mountains are the three areas that we focus on for this mountain weather page. So that's what I got. So what do you got on your minds? Any questions, comments, or that? So you go first. Yeah. So say the question again. Sorry. Yeah. No. Yeah. So the question. Oh, definitely. Yeah. So the question is the planet warming, and does that affect our models? And most definitely. I mean, we see it in trends. It's not just urbanization. If you look at climate sites that are well displaced in the middle of nowhere, they're showing a warming trend as well. So we're definitely seeing that. Now, it doesn't mean that we can't still have cold spells. We definitely have that. What it means is the atmosphere is becoming more erratic. And so we're seeing this warming of the planet. It causes more waviness in the atmosphere. And so we get these dips where it gets colder, and then these really big ridges where it gets really warm. We're seeing patterns lock into place for longer periods of time. So when we have this waviness, that ridge of high pressure that's warm and dry sits over you for like a week or two, whereas it used to move on after a few days or something like that. So that's how it's affecting the atmosphere. The models, the dynamical models that use like calculus equations to predict the weather that we look at every day, definitely they're catching on to it. They're showing us these, what we would think would be like, oh, there's no way it's going to rain that much scenarios. And we're like, that can't happen. But the model actually got it. And yeah, okay, that atmospheric river did actually produce that much rain. Or it did, the other one was the Pacific Northwest heat wave. Remember when it hit like 116 in Portland, Oregon a few years ago? The model's like, a week out, we're showing that. And I was like, no way, right? That's ridiculous. And then it actually happened. So the models are actually catching on. They're adapting to the changing planet as well. Yeah. So good question. Thank you. Yeah. Yeah. Oh, all right.
I'm a big fan of Daniel Swain.
Yeah. Yeah.
Him, but you follow.
Oh gosh, who do I follow? There's times I just try and stay off of social media altogether. Not lately. So I follow. I don't necessarily follow anybody. I just sort of wander around. I don't have a good answer for you on that. Obviously, I'll plug our social media at the Weather Service in Reno. I think we do a good job of that 7 to 10 day forecast type of content. Daniel Swain is really good at looking at events and classifying them in like, how has climate change affected these events? How unusual is it? How rare is it? I think another good one is Capital Weather Gang. They're based obviously out of Washington, D.C., but they handle a lot of issues globally and across the U.S. So they know how to communicate really well, put it in plain language, things like that. So it would be another one to take a look at. Yeah. All right. Finally. Yeah.
This is a question rivers that you talked about.
Yeah.
Coming up from the tropics and everything. My sense of it has been that they tend to be warm.
Warm, yeah.
But you said a couple of times that that it can be associated with snowfall. So I just want to get clarification.
Yeah, no, really good question. So the question is, ARs are generally warm. Remember the term pineapple express? That's what everybody called them. Yeah, and now it's atmospheric rivers. That's the politically correct term. No, you can use either. I don't care. But they warm. So why are they such a good producer of snowpack? Well, a lot of it is the rain snow lines, even in atmospheric rivers, even if they're kind of warm, is still 7,000–8,000 feet. So there's still plenty of real estate above 7,000–8,000 feet to pack a ton of snow on. And not every AR is the same. They may come out of the tropics, but some actually feed in. They'll get enough of a cold air push from the Gulf of Alaska. It'll kind of mix together. So you get an AR that maybe initially has 7,000–8,000 foot rain snow line, but it actually, that cold air comes in and all of a sudden just drops to like 6,000–5,000 feet. So you get just tons of heavy wet snow, even at lower elevations. So I think the key answer is not every AR is the same. Many of them are of the warm variety like that, but a number of them can have cooler conditions as well. Yeah, it's actually one of the tricky things to forecast sometimes. Yeah.
You're talking about the 8 different models. Got the impression that there might be more models beyond the 8. Who does them and why are they different?
So talking about the eight climate models that I'd shown earlier for the February, March, April prediction, kind of who does them. So a lot of them come from, like the Weather Service runs a couple of them. A lot of universities run these models as well. They all have different calculus equations in them. They all have different physics. They all have different initial conditions, different resolutions. So some of them are high resolution where they can even pick out mountain ranges, whereas a lot of them are low resolution enough where they'll know the Sierra and the Rockies are there, but they're really smoothed out, that kind of thing. So that's where those models, it's like you have to look at almost a multi-state scale for the trends, because if you're looking at microclimates and things like that, it's not going to pick those up. So each of the models has strengths and weaknesses, and so we tend to look at it as an ensemble approach. We put them all together, and then we run some statistics to be like, okay, what percent of the models show a certain scenario, and then that's the best guess we have. It's like, okay, 70% of them show us being dry this winter, so our forecast is going to lean in the dry direction. So that's where we are. The seasonal prediction, I like to use this phrase, seasonal prediction is where day-to-day weather forecasts were like 30–40 years ago. Remember back then where it's like you wouldn't trust a 3-day weather forecast if your life depended on it, kind of thing. And now it's like, if the forecast goes amiss, it's like, whoa, what happened? Like, I think it was Monday morning down in Reno, we had some rain in the morning. I'm like, wait a minute, where did that come from? I'm a meteorologist. I run the damn place. And it was like, where did this rain come from, right? So sometimes it does still surprise you, but it generally is an exception. But these seasonal predictions are pretty basic at this point. They're getting more skillful, but long ways to go. Yeah.
So I once read that the differential temperature between, let's say, the North Pole and let's say the U.S. Canadian.
Okay.
That decreases the jet stream strength goes down. Is that true?
Yep. Sorry, I'm a little parched here. So the question is talking about the temperature differential between, let's say, the U.S. and the North Pole, and is that affecting the jet stream? And you bet it is. That is the whole basis for kind of my answer to your question about what the jet stream is doing. So the jet stream is operated on temperature contrast. So, in theory, the poles should be cold, the mid-latitudes warm, the equator really warm. And it's that temperature difference from north to south that actually creates the jet stream and helps it move from west to east at more or less kind of a constant latitude. Well, as that temperature contrast has decreased, the jet stream also weakens, but as a result of weakening, it actually becomes much more wavy. And so that's where we see these kind of extreme weather events occurring more frequently, is that waviness in a jet stream brings extreme conditions. So it brings really warm air much further north. It brings really cold air much further south than normal. And so it's those new temperature contrasts that drive a lot of the extreme weather that we're seeing.
that's not strong enough, then low pressure systems or high pressure systems, they don't get knocked out. You know, they tend to stay. They don't get knocked out.
That's exactly, and that's, we call that blocking, is the official term, where basically the atmosphere just stalls. You know, these lows and these highs just sort of stay in place, and so that's where you see those. You've probably seen articles like in Pakistan of these huge floods because the low just sits there for days and days and days. And even here, our biggest flood events, our biggest storm events are when the ARs and stuff just lock into place and just kind of keep hitting us. I'm sure you've all heard of arc storm, which is what happened in the mid 1800s. It will happen again, where it's like for weeks, storm after storm. And that's just the locking pattern there. Yeah. You had a question? Yeah.
On the scale of 1 to 10, 1 being least scared, 10 being the most scared.
Okay.
Your personal stance on the impending doom of climate change in our lifetime.
Oof. Yeah, no. So, yeah, no, yeah. So the question is, on a scale of 0 to 10, you know, how scared am I on climate change in my lifetime? So, you know, I'm going to get a little personal here on this one. You know, I see the fires in California, and, you know, I've got a 9-year-old and a 6-year-old, and this may sound just wrong, but it's an honest emotion. Sometimes, like, should I have had kids? Right? Because I'm just like, what the hell kind of world are they going to have? You know, I mean, we're seeing this stuff now. Look at Los Angeles. Look at, you know, just some of these events in the Carolinas this year. So, long story short, I'm not going to say 10, but I'm going to go 8. You know, I'm just like, geez, you know, I'm 47. I've hopefully still got some time left. You know, what the hell am I going to see in the rest of, you know, and then my kids. So I'll go strong 8. Yeah, yeah, yeah. Back. Oh yes. What do you got? Oh gosh, you're putting me on the spot here. Let's see here. So usually, so I showed you some models that showed toward the end of January or February, it might open up again. But then I also go personal too. It's like, when am I going to travel? Or when do I have a really long run plan? Then usually you can game on. It's probably going to snow or rain then. So let's go with January 27th. How about that? That's that good for you? That good for you? Okay, there you go. All right. What do you got?
What extent do you see the impact already, or the future impact of different either the models form or like how quickly they.
Got it. So the question is focusing on the impacts of AI on modeling, specifically like seasonal weather prediction. You know, so the seasonal weather prediction piece, I can't talk to a ton. It's not where my expertise is super deep, but in the day-to-day weather forecast realm, you know, the 7 to 10 to 14 day, we're already seeing huge advances based on AI. ECMWF, the European Center that does the European model that everybody knows about because of Hurricane Sandy, they have an AI model that's kicking butt. I mean, it's not perfect, but it's something that we've, even in the Reno office, we started looking at it pretty regularly for the long range 7, 10, 14 day outlook. Like, oh, is the European AI model show, you know, kind of confirm this potential AR coming in to the West Coast. And so it kind of helps with the confidence boost. So yes, it is already here. How do, you know, it brings up the question of the role of the human in weather forecasting, and like, you know, all these students going into meteorology school, should they even do it? Is a computer going to do it all? And so my answer to that, and you know, kind of going off a tangent here, but I think it's relevant, is yes, the computers are going to do most of the work. In fact, even now, I think the computers do 70–80% of the work to do a day-to-day weather forecast. But it's those unusual situations. It's the mountains. It's the topography. It's the past experiences that a meteorologist can only bring you, that's lived here for long enough, and that takes you that 30% to the finish line of a weather forecast. So a spot weather forecast for a wildfire that might be totally dependent on terrain, really microclimates. An AI model is not going to necessarily pick up on that. but that's something a meteorologist can do. So yes, still go to school, study meteorology, learn the science, learn the physics, but your job is probably going to be different. In fact, ours is already changing. You're going to be spending more time communicating the weather, more time helping people make good decisions. What are your threshold? What is your threshold of pain of driving over Donner Pass? How much snow do you not want? Well, I can help you with that, that kind of thing. So kind of a tangent, but related to AI. It's already here, and we're seeing it. Yep. Yeah. Oh. Yes. The wavy thing. Yeah. Yeah. Mm. All right, so the first question was on the polar vortex, and I was doing my hand wavy motion, and so that is actually related because when the jet stream does more of this, it has the ability to carry all that super cold air from the Arctic down into the mid latitudes, and that is what had been termed the polar vortex, is all this cold air coming down into the U.S. that's usually up further north. So that is something we probably will see more frequently with time. Even as the planet warms, we are going to see these intrusions of really cold air go pretty far south. Now this is many years ago, probably in a different climate, but my first year at the University of Wisconsin-Madison, I lived in Southern California, went there for school, was in the mid-90s. Even the locals said this is a terrible winter. And I was like, oh my God, where have I moved to? And so that it probably was the first polar vortex there. Whereas, from Los Angeles, right, we just dump water in our radiators, right, and in our washer fluid. Who cares? We don't need it. Well, I go to Madison, Wisconsin. It's like, shouldn't have done that.